Welcome to this first lecture video for Physics 4A. In the set of lectures in this video, we will cover a few introductory topics as we start learning physics problem solving approaches. We will talk about units and how our approach contrasts with how you may have seen physical units handled in the past. And we will follow it with a short discussion on physics problem solving. In the rest of the video, we will cover vectors, vector algebra, and an example of calculation taking measurement uncertainties into account. I think a lot of people have seen units in previous science class, or you have some basic idea that when you're counting physical quantities, there's some reference size of thing that you use to count things. So I think that's the way in which you have seen units, and I think as far as um, intuitive idea of unit goes, that's good. You know what inches are, you know what centimeters are, and what I want you to go a little bit deeper is the importance of units in physics. As you might know, physics is the fundamental science, and we have a very particular way we handle units that might be different from how you have seen units handled in biology or even chemistry classes. So your textbook, I mean, section 1.2, it gives these SI base units. And what I really want you to focus on are these first three. These are really the fundamental units. And it's actually amazing that of all the physical quantities that you can measure in the world, you can boil them down to these three. Let me copy this into a note so that I can talk about it in more depth. So this is the claim I'm making that I want you to pay attention to. In chapter 1 of our general physics, we are introducing these three units: length, mass, and time, in meters, kilogram, and seconds that you might be familiar with already. And the claim I'm making is that in physics, these three units are really all the units that we need. I want to draw a contrast. Think about, for example, unit of pressure. I think this is a unit that you might have seen in chemistry. So if I'm trying to think back to my chemistry class, I think I remember learning about this. I learned about a unit of atmosphere, which can be expressed in unit of torr, which is somehow equivalent to millimeters of mercury. And I think there was one more, kilopascal, 101.3 kilopascal. I may be misremembering it. You should look it up to be sure. Um, so this might describe the, I don't know, chemistry approach to units. So to talk about one quantity, pressure, you've heard quite a few units: atmosphere, torr, and pascal. And maybe you don't need all of them. And I guess chemistry is a fundamental science. So what? Uh, so the so the way of representation that a chemist emphasizes values will be different from how we physicists like to emphasize and represent. And to draw contrast, in physics, we prefer not to introduce any new units, and in some fundamental sense, we don't. I mean, we do use unit of Pascal. That's the most preferred unit in physics to describe pressure. But how we describe this Pascal is in terms of length, mass, and time. And this is how you will see us do it. So if we have quantity of pressure, pressure is actually related to other physical quantities. It's related to force, and it's related to area. Pressure is a force per area. I think we covered that towards the end of the semester. And I think you know enough geometry to know that area can be represented as product of two lengths, length times another length. But you might look at force and say, oh, so force is a quantity that we would maybe need a new unit to express it in. And it's the amazing thing that you learn in physics, that force can actually be expressed in terms of these three basic quantities. So in a couple of weeks, you are going to learn about Newton's second law, which says that net force is equal to mass times acceleration. So mass is one of the quantities that we already have a unit for, kilogram, and acceleration is another quantity that we can express in terms of length and time. So we'll cover it in the coming week. Acceleration is, oh, how do I say this without calculus? I'll just say change of change of position per change of time, which is velocity per change of time. So all of this put together, I guess if you are just interested in the quantity, the unit of acceleration, what we would say is the unit of acceleration is unit of length. That's the same unit as unit of position per unit of time squared. So to wrap it all up, to describe the unit of pressure, we can describe it as this combination of length, mass, and time units. The combination is, so one factor of mass in the force times, so I have acceleration, so one factor of length. And in the acceleration, we have two factors of time dividing, time squared. So that's a unit for the force divided by area. So that would be two factors of length. So length squared. So that's a unit of pressure in terms of the fundamental units of mass, length, and time. Now, we are going to be working with SI unit system quite a bit. I think it stands for System International. It's some French, or it means international system. So in the SI unit system, it's constructed in a very peculiar way. That peculiar way is that whenever you have derived units, so for example, pressure comes in unit of Pascal, and Pascal is one of the derived units. Derived units are constructed from these fundamental units by simple multiplication. So I can say 1 Pascal is equal to 1 kilogram times meter per second squared, also per meter squared. Oh, so if I simplify it a little bit, canceling out this, I can say 1 Pascal is 1 kilogram per second squared per meter. And within the SI unit system, we deliberately constructed these derived units so that we don't have to worry about what this factor will be. It'll always be 1. And this is a contrast to more customary unit system where one atmosphere, how that relates to other basic units, you have to memorize it. Same deal with the torr and millimeters of mercury. So the main reason for having the SI unit system is to make this derivation process simple. So that as long as you know how these physical quantities relate to each other, from knowing this, you already know how the units will relate to each other. So your textbook spends some time covering these basic units of time, length, and mass. It's interesting history. I recommend that you read through it. And I guess we don't have time to quite talk about it in depth. But one thing I want you to put it on your radar is something called dimensional analysis. Let me spell it out. And you will see examples of this throughout the semester. I guess at this point, I will just say this much. It's a way of validating your mathematical expressions by taking careful look at the units that your physical quantities are expressed in. So you might call it analysis of units. And it's a very powerful tool that whose importance you will recognize more as you go into higher levels of engineering and physics. So I want you to talk a little bit about physics problem solving. In my years of teaching physics, I think this is the one aspect that I find a lot of students struggle with. How do I best describe it? So your textbook has this wonderful section that gives general description on problem solving strategy that you should try to employ in physics. And so I highly recommend this section. Read it through it, and and I really do want to emphasize the amount of creativity that goes into solving problems, both the physics and other problems. And this is really the skill that we are trying to teach you in this class. It's the perhaps the one transferable skill that you learn in a physics class. It's even more important than laws of physics that you might learn. Maybe not quite as much this semester because we don't teach you many laws of physics in Physics 4A. So this section gives you some general steps. Examine the situation to determine which principles are involved and make a list of given, identify what needs to be determined, and determine which physical principles can help you solve the problem. And for some of the situations, for example, force analysis, will be giving you very specific steps to follow in order to apply the Newton's laws to a particular dynamics problem that you're trying to solve. But even as we are about to, well, in a couple weeks, about to introduce the more specific steps of physics problem solving, I want to highlight that there's a very general approach to problem solving. And you can kind of see it in this section. When it gets to solution, they actually describe it in one paragraph. And it's really because the most difficult part of physics problem solving is coming up with the equation to solve for. So, in the the first step of the strategy, which will end with you writing down most often a system of equations with some number of unknowns that you solve for. That's the step that requires the most creativity, most experience, and perhaps most patience to solve through. And once you have a system of equations, the solution step, it's basically math. I'd like to say then the rest is algebra. Or solution steps are often uh, sometimes solution steps can be difficult, but very often it's easy to automate. So you will see me from time to time using computer algebra system because computer algebra system like Sage Math can solve through those system of equations much more quickly than I can. Now, what Sage Math cannot do is come up with those system of equations given a physical situation. And I would say, even though I would say, so physics class is probably the one class where we place the most emphasis on this approach to problem solving. This physics 4A class, that's basically the whole class, or maybe three-quarters of the class. So even though general physics class like this one is the one class where you will see the most emphasis being placed on developing problem solving skills, I want to give you some point of comparison so that you can see that we aren't the only ones doing it. that you can say that these are transferable skills. So I was going through a Calculus 1 textbook, for example. Let me bring it up. Yeah, so this is Calculus 1 textbook, and I think I remember something about related rates and some of those problems relating to related rates looking more similar to general physics questions. And so, this is like a chapter and a set of questions in a calculus textbook. And I hope these look kind of familiar. And a lot of math questions are basically that math questions. They ask you to do some math stuff. And without saying that those are easy stuff, the kind of questions or problems that I want you to see are quite similar in appearance to physics questions are these. So you might remember some of questions like this in your math class. There's a question that describes a situation. A car is being compacted, it's rectangular solid, volume is decreasing. Oh, at some rate, and I guess that's what related rates are. So think back to questions like this. I think these are usually described as word problems, and the kind of skills you need in solving these questions, they are quite similar to the skills that you need in solving physics questions. And and yeah, physics problems are basically like a lot of these questions. And when I was math student, I really enjoyed these word problems because I like talking and I like words. But I do recognize with a lot of students, sometimes it's these word problems that you remember having trouble with, and maybe this is the most encouraging thing that I can say. As you go into becoming an engineer or a scientist, the number one skill that you will be most valued for is your problem solving skill. That's the one thing that really can't be automated. And it's a skill that you have to learn at some point. And I strongly encourage and recommend that you focus on learning the skill in this semester in Physics 4A. This is the semester to do it. That's really the number one thing that we'll be putting most of our efforts to, and we'll be there to help you every step of the way. So that's everything I want to say, except to maybe point out one resource. There's a book called The Portable TA. Let me look it up. It's out of print. Um, I guess this is the library link that I'm using. We do have it available within the course with the author's permission, and you will see us referring to this book quite a bit. So the reason this is one of the main resources for this class is really with the problem solving, as your textbook says, there isn't one set of steps that'll work for every problem. It's a more general uh, soft skill that you will have to develop. And one of the best ways to develop skills like that is by looking at lots of examples. And your homework questions will provide some of these examples. And the portable TA is one place where you will see a lot of examples with the solutions provided by the author. Vectors are used to describe a quantity with direction. As we cover physics, you will see many physical quantities with a sense of direction. That is, when you change direction, maybe rotate around a little, the sense of the quantity changes. There are quantities without a sense of direction. We call them scalars. And you can represent them with just numbers. Some examples of scalars you might know are properties such as temperature and volume. But soon, you will see vector quantities: displacement, velocity, acceleration, and force to start. A vector as a mathematical quantity is best described as an arrow. With this arrow, I can change its length, I can change its direction, or I can change both. Note how to describe this vector in two dimensions, I need two numbers. These two numbers can be its length, 33.8, and its direction, 34.2 degrees from the horizontal. And this is very intuitive in our description of vectors as geometric quantities. But we will soon find that this way of describing vectors can be very limiting. And we are going to want to describe vectors by its components. Sometimes we say we are breaking vector into its component when we describe a vector by its two independent components. This illustrates a vector with its components. We call them components because by adding them together, we can get the whole vector. So how do you add vectors, arrows? It's easiest if you think of these vectors as representing a kind of a change. So imagine this first vector as representing a change, taking you from some starting place to this place. And let's say you have a second vector, which represents a different kind of change that takes you from one place to another place. Then to add these two vectors means you apply this change first, and from the place where you ended, you apply the second change. Sometimes this is called a head to tail method because of what it looks like. You are putting head of the arrow to tail of the next arrow. And the overall effect of these two, one after another changes, is that you have a total change that takes you all the way from the initial starting place to the final ending place. So this vector is the sum of these two vectors here. And this vector has been represented in a special way. The two vectors that add up to this whole vector, they are in two perpendicular directions. This vector here is parallel to the x-axis, and this vector here is parallel to the y-axis. And you can see that adding this vector that's parallel to x-axis to the vector that's parallel to the y-axis gives you this whole vector here. So this is the x component, and you can see in the number here that it has length of 28. This vector is its y component, and you can see here that it has a length of 19. And when you look at the whole vector, it has the components, x component of 28 and y component of 19. And these vector additions, you can swap the orders, and you see that you get the same result if you add these two arrows in any order. And actually you can use the component display here to show how those vector components appear. So this is one style of representing components, and this makes it clear as to how this whole vector is broken into two x and y components. This is another way of representing it. It shows more clearly that the x component plus y component gives you this whole vector. So for a good while in this class, as we go through kinematics and dynamics, we will work with the vectors by working with their components. And as you look at this right triangle, I'm hoping you will be reminded of your trigonometry, how to represent this hypotenuse in terms of the length of the legs, and how to get this angle here if you know some of the sides of this right triangle. You will have some homework problems that will give you some practice on switching between these two representations of the length and direction or by components. So your textbook section, section 2.1, it covers most of the things about vectors, the new type of mathematical quantity that we introduce. You might have seen vectors in your other math classes. I have to imagine it's covered in Math 3C for those of you who are already to multivariable calculus. I don't know if it will be covered in earlier math classes. Some aspects of what you'll see me talk about now in the next 10 to 20 minutes, it would have covered in trigonometry class. What's new in our class is the introduction of vectors, the conceptual aspects of which I talk about in this lecture. So what we'll cover now is more formalistic approach, more about the notations of vectors, some of the algebra you do with the vectors, and some of the calculations you may need to do with the vectors. So within this textbook section, they introduce this notation that you will see used for vectors. And this is a kind of and I want you to highlight that as to ask you to watch out for this convention. So whenever you see a letter with an arrow on top, that's our notation, meaning that this is a special kind of quantity. That's a quantity that has magnitude and direction. And the mathematical properties of this is different from the numbers you have been dealing with, scalars. So you want to pay close attention whenever you see a letter that has an arrow on top. Now, when you look at different textbooks, some textbooks will use different notations. There are textbooks that use just the boldface to indicate vectors, no arrow. Just boldface means vector. This is kind of one of the reasons to read the textbooks from cover to cover, so that they usually explain these things at the beginning part of the textbook. So you know the convention for the textbook that you're reading. Some other typeset content won't have the bold-faced part, just have the arrow. And I think this expression here, it kind of illustrates that well, this kind of notational compactness. So in this single expression, you have a vector, a letter with arrow on top. You have this absolute value sign, which is a shorthand for the mathematical operation that you are going to do to take just the magnitude of the vector. It has some relation with the absolute value that you've been working with the real numbers, but not 100%. They are related, but not the same. But this absolute value symbol means you're taking the magnitude of the vector. And once you've taken the magnitude, it's no longer a vector. That's why the quantity on the left-hand side, which is equal to that, is a scalar. It no longer has the arrow on top. So you will see that as you see me write vector-related quantities, if I'm writing it down, its magnitude, you'll see basically the same letter without the arrow. That means the magnitude. There's a kind of compactness there, which can be confusing until you get used to it. Once you get used to it, it's super convenient. So, so yeah, that's vector notations, and I think I want you to talk a little bit about vector algebra. So let me just um, write down some things that you can do with these new mathematical quantities. And in the other lecture, I already covered the kind of the conceptual idea, how to do the visual vector algebra. So here I will do as little of that as possible and just stick with just the writing down of symbols. I will try not to use the drawings and pictures, which is actually hard for me. As a reminder of what we mean by algebra, this is kind of what we mean by algebra. So you've been dealing with the numbers, so I'm gonna let A, B, and C represent numbers, real numbers, or they could be complex numbers too. Numbers. Then there are some kind of operations that you could do. When we were covering arithmetic, you could add them, you could subtract them, you could multiply them, and you could divide them. And as we focus more on the more abstract ideas in math, I want you to start thinking of these operations in a way where this addition and subtraction, they're actually not that different from each other. It's really one operation, addition. And the multiplication and division, they are property wise, they are actually not that different from each other. So they are just one operation, multiplication. And there are some algebraic properties of numbers that you've been dealing with. Like if you have some number plus another number, you know a list of properties that's associated with that. They are associative, meaning you can do this or you can do this, and the end result is the same. That's the associative property. They commute with each other, meaning this addition is the same as this addition, and so on. There are those properties. And many of the properties you had for addition, they also apply to multiplication. Scalar multiplication is associative, they commute. The one relationship where you have seen, you see both addition and multiplication together is this operation where you have an addition and you have a multiplication. Then they have what's called distributive property. This multiplication, it distributes into each term in the addition. So it becomes A times C plus B times C. So what makes multiplication different from addition other than the prior order of operations? One would be this distributive property. What we call multiplication or product are the kind of operations that will obey this kind of distributive property. And the what we will call addition. Guess in this class we don't have other more complicated ideas of addition that you might see in linear algebra. But whenever mathematicians call a binary operation addition, they are thinking ahead to some kind of distributive property. If the operation doesn't have this kind of distributed property, they won't call that operation addition. So, um, so yeah, this is kind of the reminder of the scalar algebra that hopefully you feel comfortable with. Maybe not in these exact abstract terms, but it's something that you have seen before. So when we talk about vector algebra, what we are looking at is, okay, so we have these vector quantities. Let's say A, which is going to be a vector, and B, which is going to be another vector. Then what kind of algebra operations can you do with these? And you have seen in the other video that you can do addition. I can do A plus B. And in the other video, you've seen me add these visually. And if you're trying to do further algebra with these, other than just writing this down and calling it C, you kind of need more details about that. So I will demonstrate in a little bit how to add these by components. You kind of need their component breakdown to do algebra with them in a familiar way. So we'll hold that off until a little bit. And let's see, just a few minutes ago, I said I want you to think of addition and subtraction as being the same type of operation. And what I mean by that is if you have A minus B, as far as their algebraic properties go, we can treat them in this way. A plus a vector that I'm going to call minus b. And I think in order to talk about objects like this, I need the idea of scalar multiplication. So let me introduce one more mathematical object on this page. I'm going to call it lowercase letter c, no arrow on top. So this is a scalar. And you can multiply a vector by a scalar. In some sense, I think it's the idea is kind of simple and intuitive. You know, imagine you have I don't know, b times C. Or that dot could get confusing later on. So let me just write it this way. C scalar times B. So what this would mean is, so in graphical terms, if you have a representation of your vector, like this B, then and C is a number, then what C times B would be is, well, it's a vector that points in the same direction as B, and its length is C times the magnitude of B. So that's how we would visualize scalar multiplication. And and to make sense of this particular expression, I guess my C has to be -1, so it's less than 0. So I can kind of have a convention what it means in these visual terms when your scalar factor is negative. I guess the natural thing to say is, oh, it points in the other direction, 180 degrees the other way around. So this would be if so let me just, in terms of length, just say absolute value. This would be where C is negative. So with the introduction of this idea of scalar multiplication, or the term scalar multiplication can be sometimes confusing because we have something called the inner product. Sometimes we call it scalar product. So if I want to be super clear what we mean by this, I could say multiplication by scalar factor. That the two mathematical objects involved in this multiplication is a vector and a number, not not two vectors, which we are kind of skipping this week. So so with the introduction of this idea of scalar multiplication, we can re-express any subtractions we see in this form, and we can treat it like addition. So um, so yeah, I think, and that's the extent of the vector algebra we'll cover for now. Your textbook, chapter 2, it does cover additional algebra that, deals with this multiplicative things. They talk about dot product, A dot B, and they talk about cross product, A cross B. And we'll skip those for now and just um, come back to it later as we use these in physical context. For the purpose of homework that was due last night, really all you needed to know was the dot product. A dot B is A times B cosine theta. And I covered this in the other video that's associated with that particular question. So you can look at that. We'll come back to this. So the dot product becomes important when we introduce idea of work and energy. So we will do a more proper coverage of that product then. Until then, these are the product things that we are skipping for now. So yeah, since we are skipping the product, really the only vector algebra we are dealing with is addition. And so I said to talk about the addition, we really need to introduce components so that we can add them by components. So let me use the remaining 10 minutes to talk about those vector components. By the way, there's a fat simulation that's really useful in visualizing all this and also maybe generating some examples. You can look at it on your own. It's linked from here. It's this vector addition fat simulation. It's updated version of this simulation. And in this simulation, you can kind of visualize it for yourself, what I'm gonna talk about in a little bit. So you can, drag vectors in here, manipulate it, see how the magnitudes relate to the length of the vector, see how the angle relates to, well, the direction of the vector, and how the components relate to these. So these are the things that you can look at. And I guess it's mostly visually. I hope self-explanatory. The one convention to get used to is the notion that vectors don't change when you translate them. Because so this is what you covered in trigonometry. So in trigonometry, given a point on an xy plane, you've learned to express it in different ways. Those are going to be the components that we are going to talk about. And so, looking at this vector, someone might naively think, okay, the vector ends here. So I have this component, but they don't match up here. And that's because when we talk about vector, we're really thinking of an arrow that starts from somewhere and ends somewhere. And what we care about is that change, not where it ends, just as an absolute quantity, but from where it started to where it ends. That's what we care about. So if we want to kind of have some bridge that connects to what's covered in trigonometry, imagine all the vectors as if their tail is at the origin. Then what the tip is doing in trigonometry terms will match with how we describe vectors. And just to remember that when we have two vectors that are basically translated version of each other, they are the same. Like for all intents and purposes, they are the same. We treat them the same, even when they are like all, when they are moved off and translated from each other. So I wanted to just point to that so that you have something to play with and generate additional examples for yourself. Let me just do the remainder by hand. So let me just quickly sketch out what I might have kind of lectured through more slowly. So this would be vector coordinates. And I'll just go through a little bit quickly. So all this discussion is helped by defining a coordinate axis. So an illustration of 2D plane, an XY plane that you have seen in geometry, trigonometry is very useful. And as a reminder, we kind of divide up this plane into four regions, quadrant 1, 2, 3, and 4. And sometimes you might see me refer to those quadrants. If you don't know, then that's fine. That's one superior quality of drawing is that if you draw a vector, then you don't have to say second quadrant. You can kind of see where it is. So let me say that this is my A vector. Then the vector components would be these two smaller, two vectors along the x and y direction that will add up to be this vector. So this is my x component of A vector, and this is my y component of the A vector. And when we talk about converting from, so this vector has a polar, you can give a polar coordinate representation for this vector. It has some length, a, the radius from the origin that the vector ends up at, and it has some angle, theta, that by convention, we always measure from positive x-axis that the arrow is pointing towards. So that's the parameters of polar representation. And the Cartesian representation of this point in the xy plane would be these components, the x and the y components. And the kind of the shortcut that connects these polar representation to the Cartesian representation is the right triangle. And that's really what you will see emphasized over and over as you see similar types of situations in later content. So by right triangle, I mean this triangle. It has got right angle here, and there are some inner angles that you gotta figure out. So I have this phi, which is I guess 180 degree minus theta, and so with this right triangle, you remember so ka toa, which is the kind of mnemonic for sine of an angle. Well, let me use phi since I'm using phi for this acute angle. Sine of phi is the opposite. So in this case, ay over the hypotenuse, in this case a. And ka is the mnemonic for cosine of phi, is the adjacent of the angle divided by hypotenuse. And toa is the mnemonic for tangent of phi, is opposite ay over ax. If you remember all these from your trigonometry and geometry class, that's all you need to convert between the polar representation and the Cartesian representation. And sorry, I'm out of time to do more detailed examples. I might do that separately in probably future semesters. Um, but what's potentially more challenging is the conversion from the Cartesian coordinates to the polar. Because going from the polar to Cartesian, it's helped a little bit by the fact that we have convenient conventions for cosine and sine functions. So when you so the for acute angles theta, this SOHCAHTOA, that's the mnemonic. That's how it was originally defined. It all makes sense. For angles like uh, angles greater than acute angle. So theta here, let's call this 135 degree. For angles like this, cosine and sine of these angles, they are meaningful. This hopefully was covered in your, I think it was covered in my geometry class. So if you have, I don't know, cosine of 35 degrees, then your calculator will give an answer. And this answer with a minus sign is meaningful because this minus sign is indicating that your x component is going in the negative x direction. And I can enter 135 degree sine of that, and you get positive of this, which corresponds to your y component. And all these other angles, greater than 180 degrees, also have meaning, also are meaningful. So if I have 200 degrees, which will give me an angle in the third quadrant, so sine of that now will be negative because it's going in negative. The y component is negative. So going from the polar to Cartesian representation is almost easier. It's going from the Cartesian to polar representation that takes a little bit more care, because when we do that, what we use are these expressions. The Pythagorean theorem, which gives the hypotenuse, the square root of ax squared plus ay squared. That's not too hard. Hopefully Pythagorean theorem sounds familiar. And what trips up people sometimes is this TOA portion, because we do have this relationship. Tangent of theta is ay over ax. So people have this um, um, temptation to say, oh, so theta is equal to arctangent of ay over ax. Let me give you a hypothetical where I have a point here with the x coordinate of -1 and y coordinate of -1. Let me just do the calculation on a calculator. So I have that ratio, -1 over 1, -1, so that's 1. And so I take the arctangent of 1 and I get 45 degrees. So this point, instead of being at, this is gonna be 225 degrees, you think it's at 45 degrees. You have to be careful because the inverse trig functions are slightly challenging in that you have to restrict to their domain to make them into a workable function. So by convention, arctangent is limited, where so that their range is limited, so that they will only give an answer within the fourth quadrant as a negative angle, or answers in the first quadrant as a positive angle, because the sine of tangent, or the sine positive or negative of tangent is negative, or sorry, positive, both in the third and the first quadrant. You kind of have to work through this and uh, do it carefully. That's, I think, what it comes down to. In the cases where this comes up in like homework problems, you will see me demonstrate, but just watch out for that. So, all right, so that's I think all the time we have. Let me stop that here. And again, I think what I would really recommend people do is practice with this. See if you can convert from the polar representation to Cartesian correctly, or Cartesian to polar correctly. This does make it a little bit hard to practice with. Well, maybe not so hard if you just not have this thing. Wait, I don't know. Think if you display the angle, that might be a little bit easier, maybe. But this is a good tool to kind of practice until you feel comfortable with doing those different things. So this question asks, to find the density of a spherical ball, its mass is measured to be this, and its diameter is measured to be this. Oh, so it's giving number and the uncertainty. Okay. What is the ball's density and its absolute uncertainty? Okay. So density, I think if you know the right geometry formulas, it's easy. I happen to have these formulas memorized, so let me just write them down. So for density, mass over volume, I need to know the volume of a sphere, and I happen to have a formula for volume of sphere memorized. It's 4/3 pi r cubed. So the question gives parameters as a diameter. So let me rewrite this in terms of diameter. So in terms of diameter, it's going to be 4/3 pi d over 2, giving me radius cubed. That's it. So plugging in numbers, I think that's fairly easy. Let me do this in Wolfram Alpha because it'll make it easier for me to plug in numbers, change things where I need to change. In the future, I want to show an illustration of Sage Math for more complicated expressions. For now, let me use Wolfram Alpha. So I'm given the mass. I'm going to use the best value given, 41.31. And I need to divide it by the volume of the sphere. That's going to be 4/3 times pi times the diameter, 3.43 divided by 2 cubed. And let me actually put in the units here as well. One of the reasons I like Wolfram Alpha is it's unit aware. So if the question had done this horrible thing of giving you grams and centimeters and ask you in units of kilograms per cubic meter, then Wolfram Alpha can actually do the unit conversion for you. It's a labor-saving device. So in this case, it doesn't matter because we are using the same set of units. So it says and this is the unit conversion I mean. So it's giving 1.955 gram per cubic centimeter. And I can imagine a lot of people getting stuck in this second part. How do you calculate the uncertainty? Because if you simply try to put in these values, more likely than not, it won't be graded as correct. You actually have to go through a calculation to get that. And there's a couple different ways to do it. Let me give you the way that's most conceptually the simplest, and then I will give you a second method that's more sophisticated, but in terms of running the formulas, is actually easier. So conceptually, the simplest way is to simply calculate, well, what is going to be my maximum density within this uncertainty. So, or this doesn't have to be maximum; it can also be mean. Just pick one direction or the other, and then choose your parameters consistent with either maximizing or minimizing this particular calculated value. So for mass, what I have to enter is going to be the largest possible mass within the uncertainty. So it'll be 41.31 plus 0.01 gram. That's going to be my mass. And for my volume, so I'm just going to leave everything else as formula. And when I plug in the diameter, so if I want to maximize this, I want the denominator to be minimized. So I'm going to put in 3.43 minus 0.02 centimeter for the diameter. All of that divided by 2 cubed. So this is the number I want to calculate. That'll give me the maximum estimated density, and I can go from there to figure out, okay, what's my uncertainty in the calculated density. So let me put in for the mass, that's gonna be plus 0.01. For the diameter, it's gonna be this, minus 0.02. Everything else doesn't need to change. Calculating, and I get 1.990. Okay, so for the uncertainty there, what I would need is, so this is the difference from the maximum possible to the average. So this, subtracting what I calculated before, 1.955555 gram per cubic centimeter. So when it does the calculation, make sure it interpreted your input correctly. Then the answer here is 0.035. So 0.035 gram per cubic centimeter. Let's plug that in and see if it says that's correct. So 1.955 as the best estimate and 0.035 as the uncertainty on that. So yeah, it says that's correct, and that's good enough for most things we do. In fact, our upcoming lab is exactly on that, errors and uncertainty, and this approach is what I would recommend in most circumstances. Now, suppose you want more sophisticated approach. There's a calculus approach that can actually simplify the formula quite a bit. Because here, in the end, it's kind of messy. It involves a lot of plugging in numbers. And there's a way to do it where it's simpler. And I guess this will be familiar to you if you've taken Math 3C. So I'm using the idea that's similar to what's going to be called total derivative. There's some changes that I will make to reflect the fact that this is dealing with uncertainty and not other things. But so what is this? So I have a rho, which is a function of two parameters, the mass and the diameter. And any uncertainty in rho is going to be dependent on the uncertainties of the uncertainties of the mass and the diameter. And the way to express that is the way to propagate that error is to say this total uncertainty in the density, it comes from the uncertainty in mass. And the way you see the influence of the uncertainty of mass into the uncertainty of density is you take the expression for density, so partial derivative of rho with respect to mass as a variable, kinda, multiply that with the uncertainty of mass. You can check within this expression that it's dimensionally consistent. The unit of these two things cancel out and I get unit of density. Now, because this is an expression with the two parameters, a function of two variables, you also have to consider the influence of the error on the diameter. So you have to add that in as well. So to do that, you do the same thing. Take the derivative of density with respect to diameter and multiply that to the uncertainty of the diameter. Now, if you simply add them, that won't quite work because with these random errors, you don't want these two errors going in different directions to just entirely cancel out. So the long explanation cut short. What you have to do is you have to add them in quadrature. You have to add them, add the squares of them, and then take the square root. If you've seen the formula for standard deviation, this might remind you of some of that, which is perfectly fine because the procedures you go through comes from the same idea. So this is the formula for calculating this error. Now you can see for here it's actually super complicated. Do I want to do it? Let's do it. I think it's gonna just take another 5 minutes or so, and I think we have time to do it. So, so I need the derivatives of this density. So let me write out the density as a function of mass and the diameter. 4/3 pi d over 2 cubed. So I need its derivative, where here it's gonna be 1 over 4/3 pi d over 2 cubed. Good. And I also need the derivative of density with respect to d. I'm going to have to use chain rule it'll be a great opportunity to review the chain rule. So I'm taking the derivative of the outside, which would give me minus 3m over 4/3 pi d over 2, 3. That outside through here, like treating this as an internal thing. And then I have to take the derivative of the inside, which is derivative of d over 2. Oh wait, sorry, that's not 3, that should be 4. That's the power rule. And then taking the derivative of the inside, I'm still using power rule. It just gives me that vector of 1/2. 1/2. So that's the formula for this derivative of density with respect to d. And I think I have everything I need to just plug the rest of the stuff into Wolfram alpha. The expression is going to look really messy, but that's why I recommended doing it the other way. It's conceptually simpler for something as simple as this, where you have to do this only once. It's not worth the trouble of aggravation of entering all this formula. So I'm going to need a square root on the outside eventually. And on the inside, I'm going to have two terms that are being squared. So this first term that's being squared, that'll have 1 over 4/3 pi times d, which is 3.43 divided by 2 squared. And I think I'm going to skip the, no, sorry, not squared, to the third power. Yeah, and actually I shouldn't skip the units because it's gonna reveal if I made any mistakes. Okay, so that's the derivative. Now I have to multiply that with the uncertainty in mass, 0.01 gram. Wait, I think I skipped something. Yeah, it should have been, so okay, I have this. I need to close this parenthesis here. That's the derivative. Multiply to that. And then square the whole thing there. Good. That's this first term. And now this second term, I need to put in minus 3 times the mass, 41.31 gram, divided by 4/3 times pi times a d, which is 3.43 centimeter, divided by 2 to the fourth power. Leave that alone. And I think I already have this closing. Okay, and before that I need to do times 1/2. So that's the whole, this derivative expression. And I don't worry about the minus sign because squaring will get rid of that. Multiply this with the uncertainty in diameter. That's 0.02 centimeter. Okay. And all of that gets squared. Okay, I think that's the whole expression. Let's press enter and make sure the units come out right. Okay, units come out right, and I get, okay, 0.034. Pretty close. So this formula uses a calculus assumption, which is valid when the errors are relatively small. These are relatively small, which is why this is within like 3% of the other value. Now 0.034, the system might grade that as wrong. Let's give that a try. 0.034. It grades it as correct. All right, the programmer must have put in enough tolerance for that. So that's another way to do it. Now, if you have to calculate a whole bunch of different values of propagate uncertainty for potentially different values of uncertainty, then this formula is great. It's easy to program into a calculator like Excel or other programming language and use it. So this is something that you might use in a kind of research setting where you have to do a lot of error propagation. But for a lot of things we'll do in this class, what I will say is that the first method I showed you, the one I could do super quickly without taking any derivatives, that's what I recommend.